All right, so kind of a bit of a review or walk down memory lane today, because today we're going to add, subtract, multiply, and divide functions. So these are things that we've done, all except for one thus far, okay? So formally, they're going to present this as adding functions, subtracting functions, multiplying functions, dividing functions. And they're going to use this functional notation. If I have one function and I'm adding another one to it, I just add them up like we did with simplifying polynomials. So if I have a 5 square roots of x and I'm supposed to add it, here's my f, here's my g, I'm supposed to add it to a negative 8 square roots of x, what am I going to get? Negative 3 square roots of x. Simple enough, right? Treat that square root of x just like you would any old variable. When we're adding them, we don't change the powers or anything. We just combine our like terms and give it the same name. So you've got an example, or problem just like that next to it on your worksheet. Subtracting functions. If we have an f minus a g of x, that means we're going to take the function that stands for f of x and subtract the function that stands for g of x. Okay? We have to be careful about our signs, though, so that we make sure we distribute that negative through to everybody. So if this is my f of x, and this is my g of x, what's my equation going to say? Or how am I going to put them together if I'm supposed to subtract them? Let's rewrite them, right? 2x cubed, 4x squared, minus 8x, plus 4. And I like to put the like terms beneath the other ones, right? Okay, let's put the like terms below it. We have a 3x cubed, a negative 5x squared, a positive 6x, and a negative 9. Those are the ones that go together, so that we're going to combine them. But what do we have to do? Subtract. So change the signs of every one in that second polynomial, that second function. Change the signs. And if you can do them in one big long problem, that's fine. If it helps you to write them vertically, that's fine too. So 2x cubed minus 3x cubed is what, Kobe? Very good. And 4x squared plus 5x squared is what, Laurel? Excellent. Negative 8x minus 6x is what, John? Careful, they're both negative now because I had to change the sign. Awesome. And a positive 4 and a positive 9 is what, Jordan? Very nice. Okay. So this is nothing different than we did last chapter. They've just now formally presented it as functions. We're adding two functions, we're subtracting two functions, we'll multiply two functions, we're going to divide two functions. Okay? The only difference that we've added is that we now want you to state the domain. Okay? And then we're going to ask you to evaluate that difference when x is -1. So we're going to add a couple steps to it. That way we're always spiraling up and getting better. So remind me, what is a domain? The values of x that you can possibly use, right? Okay. What values of x can we have? What are the numbers that we could plug into a function? Okay. So when we're talking about domains, we have to think about the two things that we can't do in the real number system. What are the two things that we can't do in the real number system? What gives you an error in your calculator? Error, right? What happens if you try to divide by 0? Error. Okay, so there's just two rules in our real number system. We cannot divide by 0, and we can't take a square root or a fourth root or a sixth root or any even root of a negative number. We can in the complex number system. In the complex number system, we absolutely can. But when we're talking about functions, we're graphing them on a coordinate plane, and we don't have the ability to show those complex numbers, if that makes sense, those complex zeros. So when we see things that cross the x-axis, those are our real zeros, our real answers, okay? So we always are graphing it in the real number system. Does that make sense? So functions like to graph functions. They like to see how they're going to behave, okay? So can't divide by 0, can't take an even root of an odd number. Okay? So far so good? So are we dividing anywhere here in this problem? Are we taking any square roots whatsoever in this problem? Nope. So we can use all real numbers. Domain is good. All real numbers. And if you want to write it in the infinity, the interval notation, what would it say? Perfect. Negative infinity to positive infinity. Okay? We'll review that because we're not sure if we've ever gotten that particular question taken off the final, right? So there's nothing wrong with writing it either way. They both work. Okay? But all real numbers, give it that extra little dash for the r, and negative infinity to positive infinity. Okay? Last step. They want us to evaluate this now when the difference was, or evaluate the difference when x is -1. So what does that mean? Plug it in. Put -1 in everywhere you see x. What's the other way we can do it? Rewrite the whole thing as, no? Oh, yes, put a +1 out in front. And you're thinking of Descartes' rule of signs. Absolutely. Okay, that would help us solve and figure out where the zeros are when did. Okay, but you're on the right track. What happens if I do this? What is this called? Synthetic division. That also will get you the answer. Okay, so you can choose whichever one you want to use. Okay, you can either synthetically divide it, or you can plug in a -1 everywhere you see x. and you'd have your answer either way. Okay? Anyone need to see either method, or can we move on? It's okay if you want to see either one. We're good? Okay. So the next example says find FG. Okay? Find FG of x. So what are we going to do here? Multiply. Okay? So if f of x is x cubed and g of x is the square root of x, we're going to take x cubed times the square root of x and get our answer. Can we do anything with that? Not really. We could make it into one power, but I think that's as simplified as we need to go. Okay, so f times g of x is this. Okay, now they want us to state the domain. What were the two things we can't do in the real number system? Divide by 0 and square root, cube root, or square root, fourth root, any even root of a negative number, right? Okay. Are we dividing? No. Are we taking square roots? We are, aren't we? Okay. So what can't be in our domain? Square root of negatives, right? Okay. That x can't be negative, can it? Everybody understand where we're going with this? So we just have to have positives. Can we take a square root of 0? What's the square root of 0? 0. So 0 is okay. We can't use -1, -2, -1/3, anything like that. So our domain here is going to be any real number such that x is bigger than or equal to 0. We can have 0 and anything above it. How would we write that in interval notation? Not negative, positive. So where would we start? We can go to positive infinity, right? What's the smallest that we can be? 0. So you can write your domain either way. Okay? Last thing, what are we supposed to do? Find the product when x is 4. So this time we can't use synthetic division. We just have to plug them in. Okay? We're going to take 4 and cube it. And then we're going to take the square root of 4 and we're going to multiply our result. So what's 4 cubed? 64. What's the square root of 4? 2. What's 64 times 2? So far, so good? One more example. Dividing functions. They tell you to find f over g of x. What do you think they want you to do? Yeah, divide. Take whatever f is and put it over g. So in this case, we want to take f of x is 4x. G of x is x to the 2/3. How do we handle that? Remember what we were doing in section 2? Like bases being divided, what do? Subtract the powers, right? Okay. The 4 doesn't have anybody to divide with, so it stays where it's at. Where's the bigger power? X is to the first, right? The bottom has 2/3. Which one's bigger, 1 or 2/3? 1. A whole cup is more than 2/3 of a cup, right? Okay. So where's your answer going to be? Numerator or denominator? Numerator. Okay. So when you take 1 minus 2/3, simple calculator thing, right? Or convert it to 3/3 minus 2/3 and we'll get 1/3. Okay. You can leave it as a fractional exponent. Or you can write it as a radical. Thank you. The 4 is going to stay the x is to the 1/3 power. Okay. Now what? Now we find the domain. Okay. So what root is x to the 1/3? It's like the cube root, right? Okay. So this is really 4 times the cube root of x. Okay. When we look at the domain, we have to see what are we doing that can cause problems, right? We can't do what? Can't divide by 0, and we can't square root, cube, fourth root, any even power of a negative. Okay? Are we dividing? Yep. What would make that 0? What would make our denominator 0? Cube root of x squared. Is this an even power? Nope. So we can take negatives, right? Okay. But what would make that denominator equal to 0? Cube root of x squared can't be 0, right? So if I square root both sides, I'll get a cube root of x. What's the square root of 0? Okay, so 0. And then if I wanted to get rid of the cube root, I would cube it, right? Someone say it. What can x be? 0. Can't have 0. Okay, so all real numbers work except for 0. Okay, x can't be 0. Anybody want to take a stab at the interval notation on that one? 1 to infinity, what about a half or a fourth or an eighth? Those be okay too, right? So we can't be 0, okay? So from 0, not including 0, to infinity works. Can we have negatives? Yes, because we're cube rooting, right? If we were square rooting, we couldn't, but we're cube rooting, so we're okay. So we can go from negative infinity up until 0, but just not 0. Okay? When we want to say don't include 0, we use an open parentheses, a regular parentheses. If 0 would be okay, we would actually use brackets, but 0 is not okay in this case. We can't use it. Okay? Last step. It wants to know what the answer is when x is 27. So this is what we got. And we want to find f divided by g of 27. So what do we have to do? Plug it in. 4 cube roots of 27 will be what? Cube root of 27 is what, Christian? Then 3. And 4 times 3 is what, Christian? Okay. Didn't have your calculator, that's why. All right. Everybody good with these? Nothing really new and earth-shattering. We're just combining a bunch of stuff that we've done before.